Hello everyone, welcome to lecture 3 of module 1. In the last lecture, we were looking at different segregations of the memory devices. We looked at volatile memories and non-volatile memories. So volatile memories, we saw that they are those memories where the data is removed as soon as you remove the power supply or as soon as you turn the power supply off. Examples of such memories are SRAM devices and DRAM devices, right? SRAM memory, DRAM memory. Then we also looked at some non-volatile memories, and in that, the first category was based on charge modulation of the gate oxide. So they looked like MOSFETs with an additional layer in the gate stack. If that additional layer is a polysilicon layer, then it is called a floating gate flash. If that additional layer is a silicon nitride based charge trapping layer, then it's called SONOS or charge trapping flash. If that additional layer is a ferroelectric material which has got an inherent polarization, then that is called a ferroelectric. So this is one class of non-volatile memories which stores the data in the form of threshold voltage, and there we sense currents. Next class of non-volatile memory belongs to the class of resistance-based memory, where the resistance changes as you apply some electric pulses. Inherent mechanism can be different, but the change in resistance is observable, and the data is stored in the form of resistances. So there we saw phase change memory. Then we saw magnetic memory. Also, we looked at these resistive RAMs or conductive bridge RAMs there. Then we also looked at how these two-terminal resistance-based non-volatile memories can be arranged in the form of crossbar array, and you can even stack them on top of each other to increase the density further. We also found out what are the characteristics or what are the essential characteristics that a good memory should have. And with that information, in this lecture, we would look at the memory market. The disclaimers remain same even for this lecture. Now, let us talk about the memory market. So memory market basically consists of two different commodities. First commodity is standalone memory, and second commodity is embedded memory. As the name suggests, this is embedded memory or on-chip memory. And as the name suggests, this is off-chip memory, right? So what is the property, or what are the properties of these standalone memories and embedded memories? So if you look at the density, as we discussed earlier also during the discussion on memory organization, standalone memories such as DRAM or NAND flash, their capacity is large, right? So their density is going from few GB to few terabytes. Whereas for embedded memories, such as your L1, L2 cache, L3 cache, and your registers, there the density is actually very small. I mean, it's some bytes to some megabytes at max, few hundreds of megabytes. That is your L3 cache. Other salient feature or other difference between the two is the technology node that we talk about. So embedded memory typically is a larger technology node. So you will have these eFlash or embedded DRAMs and all in higher technology nodes, typically going from 28 to 90 nanometer technology node. However, these standalone memory devices, for instance your DRAM and NAND, there the technology node has already scaled below 20 nanometers. Now the major thing where these industries differ is actually in terms of cost per bit or price per bit. So typically these standalone memory devices, their cost is less than $1 per gigabyte. However, these embedded memories are pretty costly. Why they are pretty costly? Because their area is large, right? We discussed that their area is large, and in VLSI, area actually translates to cost. So typically, cost is a function of area raised to power 4. So in VLSI, cost is a function of area raised to power 4. So therefore, since these memories, since these SRAMs and all, their area is large, therefore their cost is also large. So you can see that their cost is typically greater than $10 per GB, right? So the major technologies which are covered by standalone memory market are NAND and DRAM, and the major technologies which is covered by this embedded memory market is embedded flash or eNOR flash or EDRAMs and SRAMs. So these are three major technologies which are covered by embedded memories. And let us look at the key players now. So for standalone memory, you have these integrated device manufacturers: Samsung, Micron, SK Hynix, it's SK Hynix, not Sky Hynix, Toshiba, and Western Digital, which was earlier known as SanDisk, So these 5 players kind of occupy 90% of your standalone memory market. For embedded memory, the market is still, the key players are still in from the foundries. So you have TSMC, you have Global Foundries, you have UMC, SMIC, and Samsung's foundry. So these are kind of key players in your embedded memory market. So if you look at the overall, budget or overall annual revenues, standalone memory market has a revenue of $111 billion, whereas this embedded memory market has an overall revenue of $125 billion. If you look at its proportion, you can see from here that DRAM is actually occupying 55% of the total standalone memory market. The rest is actually occupied by NAND and some other memories. So it's DRAM which is actually dominating this standalone memory market, 55% of it, and SRAM, and this NAND is only 45% of it. And these 5 players occupy at least 90% of this. Whereas if you look at this embedded memory market, you find out that almost 45% of the market in terms of embedded memory is captured by these leading foundries such as Global Foundry, UMC, TSMC, SMIC. However, 55% of this embedded memory is actually occupied by Intel. And I don't know if you guys know or not. So Intel's NAND business is actually being captured by, or it's being sold to SK Hynix. So SK Hynix is purchasing Intel's NAND business. However, this embedded memory business is still in the hands of Intel. So you can understand Intel is a major player, or it's one of the leaders when it comes to embedded memories. Because these embedded memories have to be produced along with the processor, right? So these foundries basically fabricate those processors. So it is very easy for them to fabricate even these memories together with the processor. However, these standalone memories basically are produced by these integrated device manufacturers, which produce these memories. The major goal here is storage, or I would say the major goal here is to reduce the cost, to increase the density, to reduce the cost. Here, the major goal is to increase the speed of the process. That is the main difference between on-chip memory and off-chip memory, and that is what is reflected even here. Also, there is this SCM. So when we discussed about the storage class memory, we told that emerging non-volatile memories can be a major alternative, or can fill this gap between memory and storage. And it is actually bridging this gap between embedded memory and standalone memory. So this is actually SCM, which is now captured entirely by emerging non-volatile memory. And even their market share is like $0.52 billion, which is huge. And who are the major players here? So the major players include Crossbar.inc, IBM, Adesto, Panasonic, Everspin, Vbit Nano. So most of them are startups like Adesto, Vbit Nano. Everspin is not a startup anymore. Crossbar.inc, this was also a startup, but now they are being captured, or now they are being sold to some major companies. Now some major companies are actually trying to occupy them, major memory companies. So this emerging non-volatile memories, which is kind of bridging this gap between your embedded memories and your standalone memory, that's also a huge market now, and it is expected to increase significantly. The best news for us is that this processor market, or this embedded memory market, is almost equivalent to standalone memory market. So these memory companies, their revenue is almost of the same order of these foundry companies. And if you compare this with Indian GDP, which is like $2,600 billion, you find out that added together, this is like 1/10 of the Indian GDP. So you can understand that the memory market is a huge market. Now let us see where these embedded memories and standalone memories are basically used, or what are the typical consumers, or what are the typical companies that look for these standalone memory market and embedded memory market. I mean, who are the users? So let us look at that. So let us look at basically the applications of different types of these commodities or different memories. So if you talk about standalone memories, they are mostly used for industry, transportation, or automobile, or consumer electronics. So when you talk about consumer electronics, you talk about USB drives, you talk about flash memory cards in your mobile, you talk about the ROM in your mobile phone, and so on. Then it is also used for enterprise storage. That is your storage in the servers, in the clouds, and so on. And then standalone memories are also used for client SCM, like you have your hard disk, you have your DRAMs in workstation, in notebooks, and so on. Also, they are used for mass storage memory, such as your removable hard disk, right? So NAND memory is used for that. And if you talk about the density or the requirement of these applications, mass storage requires highest density as compared to this consumer electronics, where the density can be even low. So this is about standalone memory application. Now let us talk about the embedded memory application. So if you talk about embedded memory application, the major kind of the major application of embedded memories goes into this microcontroller units, microcontrollers or MCUs. So it's microcontroller units or MCUs. So what are the major goals? So all of these devices, I mean your general purpose or general home appliances, everything has got a microcontroller chip, and that microcontroller chip also needs to store some data. So what are those data? For instance, if you are talking about your microwave oven, so it has got a timer, right? And there are several dishes, inbuilt dishes fed on it. Click on this mode and you can make some, like let's say you can grill chicken with it. Click on some other mode or go to select some other mode and you can, make some tandoori item with it. So those things are actually because you have this capability of storing these data in your microcontroller of microwave oven. Even your washing machine and all, they have different modes, right? You have wash and dry mode, you have separate mode for cotton, separate mode for silk, for soiled clothes and so on. You have different modes. So all of those modes are stored in some memory element, which is basically embedded memory, which is present in your MCU. One of the largest consumers of this embedded memory is the smart card application or your SIM card. So your SIM card also has an internal memory, which actually stores some of your contact, right? Earlier times when the phones were not that smart, you would remember that they were giving you option of saving it on your SIM card or your phone, right? Nowadays they only ask you to store it on the server or on the phone, but earlier they also had this option of storing it on the SIM card, right? So SIM card also has some embedded memory. Also these smart cards or RFIDs, these also require embedded memory, and the main requirement for the memory here is that it should be ultra low power and the read should be very fast. So these are two properties of embedded memory that is actually required or that is actually favorable for applications such as smart card. Now these embedded memories are also present in your mobile devices. Like you have these MPUs, so microcontroller units are called MCUs, and your mobile computing units are actually mobile processing units are actually called MPUs. So you would hear this term MPU when you go to the industry. So what is the share of MPUs in this memory or something like that? So they call mobile phones and related applications where these embedded memories go as MPUs. Also, they are used in L3 level of cache for high performance computing systems and so on. And also they are used in SoCs, system on chips. And if you talk about the density, microcontrollers, they're the dense, like microcontrollers or these automobile systems or these general purpose devices, their size is already very large. So the density, even if it's smaller, it works fine. However, as you go towards this SoC and L3 level of cache, your density has to increase. And that is a major requirement, right? So with this introduction to the application, let us look at some of the forecasts for different memory markets. So let us first take the case of standalone memory market and let us look at the forecast for 2025. So in 2019, the overall market for this was supposed to be 111 billion, which is going to increase by with a CAGR or cumulative annual growth rate of 9%, and it will increase from $111 billion to $185 billion. Here, if you look at the proportion of different memories or different classes of memory here, you find out that almost 55% was actually dominated by DRAM, 45% was dominated by your NAND, and rest other memories like NOR, NVS RAM or ferroelectric RAM or EPROM or PCM, these were actually taking very small amount, right? However, going into the future, you may expect that the share of this NAND and DRAM would be almost same, or so as to say, this NAND flash, this NAND flash demand or NAND flash revenue would actually increase as compared to the increase in DRAM. So NAND flash is expected to increase by a growth rate of 11% as compared to your DRAM, which is going to increase only by a factor of or a growth rate of 7%. Also, the share of other kind of memories, other memories like EPROM or your NOR flash or phase change memory devices, that is also going to increase significantly. especially if you look at this phase change memory, its annual growth rate is going to be close to 42%. However, if you look at this market of SRAM, non-volatile SRAM or basically SRAM, you see that there is a reduction in the overall revenue. The thing is, companies are trying to do away with this SRAM kind of memories because they require a large number of transistors, let's say 6 transistors. And as I told, in VLSI, area is actually proportional to the, cost is actually proportional to area raised to power 4. So people are trying to do away with SRAMs even for cache. And that is the reason why people go for embedded DRAMs or embedded NOR flash, or in the future, you will be seeing embedded MRAMs for L3 level of cache. That is for sure. So this is how, the market is going to change within next 4 or 5 years. Now, this is about, standalone memory market. Let us also look at the performance of these emerging non-volatile memories, because these emerging non-volatile memories, we told that, their proportion is going to increase in the near future. And for PCM, it's going to increase significantly. But why? That will answer in the next slide. But if I say that PCM is an emerging memory, that would be injustice to it, because in 2010 itself, Nokia actually introduced PCM devices in its N series and E series. So there, the memory was actually, internal memory was actually PCM. And we never knew unless, in 2012, these companies in China, they kind of, open these chips and then they lap it layer by layer and try to find out what was the material inside. Then they found out that it was PCM. So, the companies experiment with these devices, they look at the performance, and, then only they, keep them, or then only they decide whether they want to go ahead with those products in the next generation of items or not. So that was the case for PCM. Anyway, so why is it so promising? Let us look at that. So for that, let us compare all these standalone memory devices based on certain parameters. So the parameters that I'll be comparing them on would be endurance, scalability, price, and speed. And here, what exactly these things means, these arrows, what they indicate? These are rated from 0 to 5. 0 meaning best case scenario with respect to that quantity. 5 means, 0 means worst case scenario, with respect to that quantity. And 5 means the best case scenario with respect to that quantity. So if you look at NAND flash, in terms of scalability, it's huge, especially with the advent of 3D NAND flash memory, where the NAND flash cells are stacked on top of each other. It's the densest of all the memories. And that is the reason why it's being used for SSD, cloud storage, and so on. So in terms of scalability, it's the highest. In terms of price per bit also, it's the lowest, and hence it's best with respect to price. That is why it has been rated 5. However, in terms of speed, it's pretty low, right? And in terms of its endurance also, it's pretty low. I told that it's only 10 per 5 cycles, right? If you operate it for more than 10 per 5 cycles, you're not sure whether you'll get reliable operations, or your memory characteristics will definitely degrade. So that is about NAND. Now let us talk about PCM devices. In terms of scalability, yes, they are highly scalable. In terms of cost per bit, they are not as cheap as NAND flash, but still their cost per bit is small. However, in terms of speed, they are also in terms of speed, they are also slow, somewhat on the slower side. Why? Because here you have to melt your phase change material and then cool it. Only if you allow sufficient time to cool, then it can go into the crystalline state or the low resistance state, right? So that kind of timing actually makes it, or that kind of timing constraint actually yields this kind of low speed performance. However, its endurance is actually good. It's not bad, it's actually good. Now let us look at the third candidate, which is DRAM. So for DRAM, scalability is an issue. Why it is an issue? Because you cannot scale capacitors very drastically, or I would say incessantly. You cannot continue scaling your capacitors. Also, the peripheral circuitry requirement for DRAM is tricky. It is quite complex as compared to your SRAM, that we'll discuss in this course. And because of that also, their overall area is actually larger. So its scalability potential is not that good. In terms of price also, it's average. It's not that large, but it's not that low as well. Speed is really high because you have only one transistor, one capacitor kind of cell. And also, since you're dealing with a capacitor, the endurance is high. You can work with it as long as you want. If you look at MRAM devices, the scalability is a question mark. Scalability is not that good. Also, their price is pretty high. Speed wise, yes, they're pretty good in terms of speed. And also endurance wise, people say that their endurance is infinite, but the stacks which were actually produced or which were present while this data was being made, they were showing good endurance, but not as good as compared to capacitor, right? Also, if you look at RAM, then here it shows that it's not really scalable, but it's highly scalable, because this was actually made in time where in 2019, when the stacks that were made were not that advanced. Nowadays you have advanced stacks, so whatever I'm saying, it may also be changed in the present scenario. Not that much change, but yeah, you can have some stacks showing the properties which are opposite to what I'm saying right. So RRAMs, you see, scalability is low, price is high, your speed is also low, also your endurance is low. So because of all these properties, RRAMs are not that good candidates for standalone memory, and variability is one of the major problems hindering their application as standalone memory devices. If you compare, I mean, from this analysis, PCM is very lucrative for standalone memory market, and that is the reason why it was used in Nokia phones earlier. Because this price, I mean, price is something that all the companies go for. I mean, cost per bit is low, go for it. That is what industries want. Now let us also discuss the performance of these embedded memories like entities. So let us take the case of SRAM first. All the individual SRAM cell has got like 6 transistors, but those transistors are highly scalable. We can use 5 nanometer technology transistor or 7 nanometer technology transistor, or any advanced node transistor, and utilize it for making SRAM. And therefore its potential for scalability is high, although a single cell has 6 transistors. And just because a single cell has 6 transistors, its area is large. And as I told, in VLSI, cost is a function of area raised to power 4, and hence its cost is somewhat higher. Not somewhat higher, it's actually very high. And that is the reason your amount of cache memory is limited. One is the area, second is the cost also. In terms of power, although there is this leakage power, which is high in these SRAMs, especially when you use these advanced technology nodes for realizing it, but it's lower than your embedded technologies, other embedded technologies. In terms of speed, it's the fastest, and that is why you use it close to your processing core. Endurance wise also it's large, because here you are storing these data bits in the form of charges on capacitors, internal node capacitors, and that are changed with the help of that cross-coupled inverter pair. So that is why its endurance is also very large. Now let us talk about the embedded flash memory, which is basically embedded NOR flash memory. In terms of scalability, it's not scaling as your logic technologies are scaling. For instance, the logic technology is now at 5 nanometer. There are products on 5 nanometers, but if embedded flash, the best that I have seen so far in terms of NOR flash is 14 nanometer, or most common is 28 nanometer embedded NOR flash. So I've worked with 65 nanometer embedded NOR flash and 55 nanometer NOR flash while at UCSB, but the most advanced ones that I've seen is 28 nanometer embedded NOR flash, and I guess 14 nanometer ones are also under development, but they haven't been developed. So in terms of scalability, it's not scaling as good as the logic technologies. In terms of price, it is actually less costly as compared to SRAM cell, because here fabrication technology wise, I mean, it is mature technology. Embedded NOR flash is a mature technology. They basically use split gate technology and so on. However, the price is actually lower as compared to SRAM cell because their area is smaller. I mean, the density is large. In terms of power consumption, if you look at it, I mean, in terms of power, if you see, it actually consumes a large amount of power, because flash memories, you require, large voltage pulses in the order of, 20 volts, 16 volts, 18 volts for programming these devices. So that is one major problem with flash. Another major problem with flash, right? Also, in terms of speed, flash memories are very slow. They are very slow as compared to SRAM or even DRAM. Their programming speeds are in some millisecond, like programming times are in some millisecond, read time is in some microsecond. So they are very slow. However, embedded ones are having a smaller time, like a faster speed as compared to the conventional NAND flash memory. So NOR flash, embedded NOR flash is having a programming time which is like, smaller, that is in some microseconds, and even the read time is some microseconds, so some nanoseconds. Also, in terms of endurance, as I already told, these flash memory devices, because of the wearing of tunnel oxide, 10/5 cycles is almost the maximum that a single NOR flash device can give you in terms of cycles for which it operates correctly. So in terms of endurance, it's poor. Now let us take the case of embedded RRAMs, which is a recent addition to this group. Crossbar.inc is actually working on this embedded RRAMs for its 40 nanometer technology node. So what it has shown us is that its scalability here, it's, since this was made in 2019 or something, scalability is shown to be poor as compared to eFlash and SRAM, but passive RRAM crossbar arrays, they are highly dense. But for embedded memory, we generally go for active 1T1 RRAM arrays where there is a selector also. And since there is a selector as well, what happens is the selector has to pass the amount of current required for RRAM. Now the currents required for RRAMs during forming process is pretty large. So because of that, these transistors cannot be scaled, very incessantly. So therefore, their scaling is actually limited. That is what limits its scaling. In terms of price, it's really cheap as compared to your SRAM because here density is even larger, right? Also, in terms of power, it is actually less power consuming as compared to embedded NOR flash. However, it is more power consuming as compared to your SRAM. Why so? Because in SRAM, the leakage power dissipation is there, but in RRAMs, its conductance range or resistance range is limited, and corresponding to ROF, which is in some gigaohms at max, you'll have some nanoamps of current flowing. So even that way, it's kind of less power efficient as compared to your SRAM devices. And in terms of speed, some RRAM stacks nowadays can show you speed up to some nanosecond of switching, but still its speed is actually low as compared to SRAM devices. Also, endurance wise, 10 per 6 cycles to 10 per 7 cycles is a typical SRAM, typical RRAM endurance. So even that way, it is actually better than eFlash, but it's not as good. But there are some stacks which can show even a higher endurance. So eRRAM is actually one of the technologies because its cost is actually low and it's performing almost good for all the other applications. So it performs almost average for all the other metrics, and cost is one of the major thing that I told in the in the memory industry. Cost is a major thing that they look for. So because of that, this embedded RRAM from crossbar.inc is an attractive candidate for embedded memory. Now let us also look at the emerging non-volatile memory projections for 2025. So right now for standalone memory market, this MRAM is almost 15 to 20% of the overall standalone memory market. However, PCM is 80% of that. And in 2025, it is expected to grow by 42%. However, even there, PCM is going to dominate the landscape. We expect RRAM to enter this landscape along with MRAM with the developments in RRAM stacks. So standalone memory also, RRAMs could be a key player there in the future. In terms of embedded memory, right now, what is the scenario? In terms of embedded memory, it's RRAM and MRAM which are into the picture. And if you look at this share, it is going to increase by 118% with MRAM dominating and RRAM being a small part of it. Reason being that MRAM is one of the major contenders for replacing L3 cache or EDRAM in the L3 cache. PCM will also enter this market because this ST Microelectronics has come up with this PCM for embedded, but I don't know how much gain it will be in terms of cost, but definitely that will also enter the market. Now let us look at the key players for emerging non-volatile memories. So let us start with embedded application. So for embedded application, Panasonic started work on RRAM based microcontrollers, like microcontrollers which had RRAM based memories. SMIC continued it, and now UMC has taken over it, and they are actually working on RRAM based embedded storage for microcontrollers. ST, as I told, ST started its PCM based embedded memory in 2020. Qualcomm, Samsung, TSMC, and Global Foundries, they have also started this MRAM. So Global Foundries, its 22 FDX process, it comes with embedded RRAM. Although that embedded RRAM is from some other industry, it's from Everspin, but Samsung, TSMC, and Qualcomm, all of these companies, beyond their 28 nanometer technology node, they have started coming up with MRAM or STT-MRAM based memory devices for embedded applications in mobile devices. Also for L3 cache, IBM, TSMC, and Global Foundries, they actually brought this eMRAM technology way back in 2000, towards the end of 2019 itself, and they are actually working with that. And for embedded non-volatile memory in SoC, this crossbar.inc is trying very hard to include this RAM for embedded memory, and they have been successful. Towards the end of 2020, they made their products. They embedded these RMs into products as well. In terms of standalone memory, for mass storage, it's crossbar.inc itself who is actually working for it, crossbar inclusive. Intel Micron, together with Micron, Intel actually came up with this 3D cross-point arrays based on phase change memory devices. So it consists of phase change memory selector in series with phase change memory. Memory and selector both were made up of phase change memory device, phase change materials. So phase change material based selector in series with memory, that was actually introduced by Intel and Micron together as 3D crosspoint or Intel Optane memory. So Intel called it Optane memory, which is its fastest memory till date. Optane SSDs, you may have heard about it. Micron called it 3D crosspoint devices, 3D X-point. However, what happened was Micron actually sold its 3D X-point this year to Intel, and now Intel is actually selling all of these things along with its SAN memory thing to SK Hynix. So that deal has not yet been closed, but it's going to sell it. It's close to completion, so that is why I'm telling you this. So these phase change materials, they have been used here for both memory as well as selector, and that is what makes it very fast. So Optane memory, which is Intel Optane, which is still the fastest and the costliest memory of Intel, it's made up of phase change memory. I guess you guys would have heard about Optane memory at least. For enterprise storage, Crossbar is going ahead with Hari RAMs, where Everspin, it's a leading company in case of for magnetic RAMs. It makes all kinds of magnetic RAMs like toggle RAMs or STM RAMs and so on. So Everspin in 2017 itself started making this for enterprise storage or SCM. For industrial and consumer electronics, Adesto is one of the companies, which is one of the oldest companies making this, conductive bridge RAM based devices since the very beginning, since 2015 itself, along with Everspin. So Everspin has been in this market for a long time, and these are kind of the early starters of this field. Adesto, CB-RAM, Everspin, toggle RAM, and then eventually going to STTM RAM. In the future, you will see some SOT RAM also. So this Everspin has also got a huge funding for SOT RAM. So in the future, you can actually expect SOT RAM as well, which are more energy efficient as compared to STT RAM. And this field is so dynamic, this memory field is so dynamic that if you open your LinkedIn, or even if you open Google News, you'll find the news every month at least. Here I've summarized some of the latest news. So MRAM, GlobalFoundries introduced a scalable embedded MRAM technology on its 22FDX platform. You have Spin Transfer Technologies, which is a startup. Everspin filed for IPO, aims to raise $45 million, which it got, and it got huge funding for SOT. IMEC is one of the leading companies which is working on magnetic memories as well as flash memories. And this Avalanche Technology is also a startup which was actually bought by this Sony. In terms of RAM, CEA Leti, France, which is National Research Lab of France, and Israeli startup Vbit Nano, they have actually collaborated. They collaborated last year to develop SiOX based RAM technology, and it's successful. They have now demonstrated a product out of it. Also 4DS memory, they kind of announced that they developed 40 nanometer RAM cell, and they're now being used by this Western Digital. So Fujitsu actually announced the launch of first 4 megabit RAM, which was largest mass density product RAM. This was 2 years ago. Panasonic actually is one of the earliest starters of RAMs. I already told that. So at UCSB, I was actually working with this Panasonic and Applied Materials, where they were actually developing, RAM based circuits in their 65 nanometer technology node. Also, along with UMC, United Microelectronics, Panasonic has decided to, develop 40 nanometer RAM technology. Extend their 65 nanometer RAM technology to 40 nanometer RAM technology for production with UMC. Also, Rambus signed an agreement with Western Digital for, RAM technology. PCM, as I already told, is cross-point devices. So Intel launched its first commercial 3D X-point memory chip, or this was done along with Micron. So you can say here that in April 2017 itself, Intel kind of introduced this Optane memory, which is nothing but phase change memory. So the material stack is such that both selector as well as memory are in series, and both of them are using phase change material. In 2019, they introduced second layer of the second version of this Optane memory. And Samsung also started its commercial production of STT-MRAM in 28 nanometer technology in 2019 itself. Then Everspin actually started 1 GB standalone STT-MRAM with GlobalFoundries 28 nanometer in July 2019. And in 2020, they also introduced this eMRAM technology, embedded MRAM technology, embedded STT-MRAM technology in their 22FDX node. Also, Micron announces cross 100 SSDs, which were actually using the same phase change memory devices. But now Micron has stopped this. Micron actually, it was not able to kind of extract profits out of this 3D crosspoint, so it actually sold it to Intel, and now Intel is selling entire NAND division to SK Hynix. This is going to be fixed in 2022. Best part, at IIT Kanpur, our group has access to this embedded MRAM devices on 22FDX platform. I mean, if you want to develop devices using embedded MRAM on 22FDX of GlobalFoundries, we have that capability. Also, we have signed MOUs so that we can develop 3D integrated RM-based ICs along with CELT and ST Microelectronics 130 nanometer technology, where the front end would be CMOS circuit made on 130 nanometer ST Microelectronics technology, and the back end, that is EVA Metal 4, you'll have RMs integrated by CELT. So we have those capabilities at IIT Kanpur. So it's a good news. I mean, you can produce these, you can use these facilities to fabricate chips. You can measure them, and you can kind of explore them for new applications. Now let us also look at the interesting case of China. So 5 years ago, there was no memory company in China. I mean, I'm not only talking about indigenous memory company, but none of the memory companies, major IDMs, had their office in China or their branch in China. The Chinese government realized that China was, 40%, like almost 40% of the memory market was present in China. So it was consumer of nearly 40% of all the memories. So that government realized, and they actually made policies to promote, indigenous memory industries and promote offices of all of these memories, memory companies in China. And as a result, many indigenous Chinese companies came into picture, like this YMTC, which is a major 3D NAND company. And also all these major IDMs have now their, offices in different parts of China. Major offices are located in this Wuhan region, which is infamous nowadays. And I guess almost everyone hates it because of the emergence of this coronavirus. But you just look at it. I mean, the government's push, it led to indigenous development of indigenous companies which are now competing with Intel. And YMTC is a very advanced producer of 3D NAND flash. It is now competing with major 3D NAND flash companies. So you can understand that semiconductor manufacturing and memory manufacturing in general is a major kind of memory market. India is the second largest memory market after China. So the government realized it recently, and that is why it said that Indian semiconductor mission and memories is one of the important parts of that. And I would really like to see some indigenous company in India making memories whose technology is also not imported, but it's developed here itself.